Is there.
All right, hello everyone. For context for the web audience watching from deeplearningbook.org, today's lecture is presented at a study group for the Deep Learning Book at Google. So you may hear some Googlers joining in with questions about this chapter. Other than that, this is a lecture for a general audience. Today we are covering chapter 6 of the Deep Learning Book. This chapter is about deep feed-forward networks. In other words, traditional neural networks that are not recurrent. But basically, this is most of modern deep learning. It is neural nets that are essentially function approximators, and we fit them to functions represented by a training set. And essentially, everything else in the book is extensions and refinements of the ideas in this chapter. Overall, we'll follow a roadmap that follows the book very closely. We'll start off with an example of how you can use neural networks to learn the XOR function, which we would not have been able to do with traditional linear models. Next, we'll look into how gradient-based learning works in general. A lot of this will be very similar to what we already saw in chapter 5, but I'll have some more detail on how it works with neural nets. We'll talk a little bit about hidden units for neural nets, and then how to design the architecture, how you actually connect those units to each other. And finally, at the end, we'll talk about backpropagation, how you actually compute the gradients that you need for gradient-based learning in these models. To start things off, let's look at the XOR problem. If you haven't heard of the term XOR before, it's short for exclusive OR. It means that if you have two different bits, the XOR function will output a 1 if exactly one of the inputs is active. It means if one of the inputs is active or the other input is active, but not both, then the XOR function will output a 1. If we look at this in terms of a graph of the input space, we can plot one of these bits on the x-axis and the other bit on the y-axis. And we see that at the lower left corner and the upper right corner, the XOR function outputs a 0. At the lower right corner and the upper left corner, the XOR function outputs a 1. This is difficult for a linear model, and in fact, impossible for a linear model, because it is not linearly separable. There's no line that you can draw that puts the 1s on one side of the line and the 0s on the other side of the line. So this is the first place that we really need neural networks to solve this problem. Other parametric functions like we saw in chapter 5 that are based on linear functions are not able to do it. In order to build a neural network, we're going to introduce a new idea of a hidden unit with an activation function. Instead of directly computing the output, we'll start by computing several features of the input, and then we'll use those features to classify the input example. Each of these features will be defined using what we call an activation function. Essentially, we make a linear transformation of the data, and then we apply a nonlinear activation function to determine the value of the feature. The activation function we'll use in this example, and the activation function that we'll use almost all the time actually, is called the rectified linear activation function. We'll call the input to the activation function z, and then we'll call the output of it g of z. The rectified linear activation function is actually linear for positive values, and then it's just 0 for negative values. You can think of this as taking the maximum between 0 and z and passing up that value as the output of the feature. This is a very simple nonlinearity. It's actually piecewise linear with just 2 pieces, and only one of these pieces will actually have values that are learned by the model. So it's very close to about as simple of a nonlinearity as you could imagine. It turns out that this is sufficient to take our models from being linear to being able to represent any function if we use enough different units connected together. We'll describe later how we can actually implement any function using this approach. But now for the XOR example, we can look at a relatively simple special case solution to how we can actually learn the XOR function. When we design a neural network, we think of them as having different layers, and we can draw them with different levels of detail. The solution to this problem is going to have 2 hidden units. So one way that we can draw neural nets at a high level of detail is to actually draw each individual unit specifically. So we'll have a hidden unit 1 and a hidden unit 2. They're both functions of our inputs, x1 and x2. So x1 is the first bit that we pass to the XOR function, x2 is the second bit that we pass to the XOR function. we're going to compute two slightly different features that represent those input bits in a different space. And then we're going to compute an output value y, saying whether we think the XOR function should output a 0 or a 1. Yeah.
So what's your intuition on why ReLU is so effective?
Oh, so my intuition on why ReLU is so effective. There's two things. One is it usually has a very strong gradient. And that means that gradient descent can actually compute large gradients. The other thing is that its behavior is extremely consistent across its whole domain. If the output of a ReLU should be 1, and that would make the model work well, but its current output value is 10, it's very far from the correct value. Gradient descent still knows how to change it to fix it. Gradient descent still knows that it should decrease its value. There are some other kinds of activation functions where if you are very far from the correct value, it can be hard to tell how you should fix it. Linear functions are really nice because one set of weights describes how they behave over all of space, and it's really easy to tell how to adjust those weights.
Okay.
Another thing to keep in mind is that there are several other functions that work very nearly as well as rectified linear units. To some extent, the reason that we use ReLU is just cultural. It was one of the first really effective hidden units that we started to use that worked really well. But we could easily have used leaky ReLUs or parametric ReLUs, or in some cases, we'll actually see that the cosine function works pretty well as an activation function. So to some extent, there may not be a lot that's special about it. It may be just one member of a very large set of different activation functions that all work really well.
Okay, thanks.
Yeah. All right, so looking back at this diagram from figure 6.2, we have two different ways that we can draw the same neural net. On the left, we actually show a separate node for every individual feature. On the right, we've kind of collapsed it so that we show one node per vector value in the network. We can either think of this as a network that has lots of individual units or neurons, or we can just think of it as a network that has a layer represented by a vector h in the middle. Most of the time, we will use this vector representation on the right when we draw neural nets because it's a lot more compact. Occasionally, we'll do this expanded view where we see lots of different individual units so that we can discuss in more detail what each of those units is doing. If we take the diagram on the previous slide and we want to use it to solve the XOR problem, we actually need to fill in specific values for each of the parameters in the network. So looking at the diagram quickly, we have a matrix that's a 2x2 matrix that describes the mapping from the X features to the hidden layer H. There's two inputs and two outputs, so it's a 2x2 matrix. And our learning algorithm will have to figure out how to set those values. We also have a lowercase w vector of weights mapping from the hidden layer to the output layer. And there's two hidden units, one output unit. So this is just a vector with two entries in it. I also haven't annotated them here in this slide, but there's a vector of biases that shift the output of these matrix or vector multiplies. So there's two biases represented by vector c here that control the value of h. And then there's a single bias of b that controls the value of the output y. We can actually just hand design a pretty good solution, or you could find a solution by minimizing the mean squared error between the actual output and the desired output. If you go ahead and do mean squared error minimization, you'll get something with a lot of decimal points in it. For legibility, I've given you a hand designed solution here where everything is just nice, simple integers. Specifically, I've set w to be all ones. So each of our features starts off by just summing up the bits. Keep in mind, we're solving the XOR problem. We want exactly one bit to be on. So if there are 2 bits, both features will get a sum of 2. If only one bit is on, both features will get a sum of 1. And then if no bits are on, both features will get a sum of 0. The next thing that we do is we define the biases for the hidden layer to shift that sum optionally downward a little bit. The first feature that we use is actually not going to shift them at all. So the first feature will literally just take the sum of both of the bits. And then the second feature is actually going to shift them down by 1. The reason that this is useful is that we're then going to apply the rectified linear activation function to it. So for the first feature, we have all positive weights. For the XOR problem, the inputs are always positive. So the sum is always going to be positive or 0. And in French, you actually call that positive, but in English, we call it non-negative. The second feature is actually going to make use of this rectified linear activation function. Because we have this negative bias term here, we can actually end up with a value of -1 after the matrix multiply if neither of the bits in the input is on. And because we've shifted the value of the affine transformation down to -1, the ReLU will come in and clip that to a value of 0. So that's the first place that we really see some nonlinearity in this network. It turns out that clipping that value to 0 will make it so that a linear classifier looking at these hidden unit features can actually solve the problem using weights of 1 and -2, respectively, on the output of the hidden layer. It's a little bit easier to see why if we look at a diagram that actually plots this in space. So in the original problem, we weren't able to draw a line separating the 0s and the 1s in the XOR problem. On this graph, we're plotting x1 on the horizontal axis and x2 on the vertical axis. We're actually looking at the bits that are the input to the XOR problem. On the right, we plot the same problem looking at the values of the hidden units, the features that we actually learned using these W and C parameters and the rectified linear function. The first feature, H1, is actually just a sum of the number of bits that are on in the input. So this 0 here gets mapped to a 0 on H1, and both 1s get mapped to a 1 on H1, and then this 0 here, which has both inputs active, gets mapped to a 2 along H1. So next, let's look at what happens with H2, the feature where we shifted the sum of the bits down by 1 and then clipped it with the rectified linear function. It turns out that this 0 over here gets mapped to a value of 0 rather than -1 down here. If it had gotten mapped down to -1, it would be kind of along a line with this 1 here, and it would be hard to separate. The 1s actually both get collapsed to the same coordinate because they both have a single bit on. That happens for both H1 and H2. And then this 0 over here has a sum of 2 bits on. It gets mapped to a coordinate of 1 on H1. Because we've actually collapsed both of the 1s to the same point in feature space, you can think of it sort of like we folded the image over and got rid of this problem that we can't draw a line separating the 1s. We put them on the same side of this thing that looks a little bit like a reflection line. And now we can actually draw a line through here with a linear classifier on top of this feature space. So this goes back to the core idea from chapter 1 of the book, that representations matter. And as we saw in the very first figure in the book, if you have 2 concentric circles and you convert the representation from rectangular to polar coordinates, suddenly everything becomes linearly separable. Here, we've done this for the XOR problem. We've actually learned a specific neural network that turns the XOR problem into a linearly separable problem. And so we've taken this idea of changing representations and we've made it concrete and formal to the point where an optimization algorithm can find the parameters describing the representation you need for you. In this case, I gave you a hand-specified solution that's easy to walk through, but an optimization algorithm could have found the same thing by minimizing the mean squared error between the desired and the actual values. Yeah.
How do you figure out how many hidden layers it will take to make things linearly separable?
Yeah, so the question is how many hidden layers will it take to make things linearly separable? We will cover the choice of hidden layers later in the architecture design section of this lecture. So the next section of both the book and this lecture is the section on gradient-based learning. In the previous chapter, chapter 5, we already saw that there's a building block strategy for making machine learning algorithms based on optimization. You can specify a model, and you can specify a cost, and you can specify an optimization algorithm, usually one based on gradient descent, but it could also be based on evolution or something like that. And your optimization algorithm will then adjust the parameters of your model to minimize that cost. The overall goal is to design the model and the cost so that the cost is smooth and the optimization algorithm is more likely to succeed. And then you just let the optimization algorithm run. So we've already seen basically how to do that. Yeah, go ahead.
Quick question. So with ReLU, there's a discontinuity in the derivative, right? Is that a problem?
Yeah, so that's a good question. Is it a problem that the ReLU has a discontinuity in it? If we actually implemented our code base so that it returned like NaN or something, if you went to the hinge of the ReLU, then that would be a problem for optimization. And a lot of the reason that people did not use ReLUs for a long time was this belief that they were a bad idea because a lot of the theory doesn't make a whole lot of sense. In practice, it turns out that if we just implement it so that we return 0 rather than NaN at the hinge, everything works fine. There's a few ways that you could justify this. One that some people like to use is that this is a form of subgradient descent, where instead of descending according to the gradient, you descend according to the slope of a line that passes below the function you're minimizing. Unfortunately, that doesn't actually quite explain what happens with neural nets, because if all you had was a ReLU function, then yeah, the values we use would be subgradients. It turns out we actually use complicated functions that compose several ReLUs together. So like if you have a negative weight in your neural net applied to the ReLU, and then you differentiate the output of multiplication by that weight, what you get in the version that we implemented in TensorFlow and Theano, that's not actually a subgradient of the new full expression where you've negated the ReLU. So the subgradient story doesn't really fully explain why it works. I have another hackier story for why it works, which is pretend that we never actually hit a real value of 0. Like we're optimizing over functions of real numbers, and we're implementing these functions in digital computers. It's very unlikely that we would actually hit specifically a value of exactly 0 for the input to the ReLU function. And so I like to pretend we're really hitting something like negative epsilon, and then the computer rounds it up to 0. The derivative at negative epsilon is 0, so if we pretend that the derivative at 0 is 0 rather than undefined, everything works out. Somebody else who's more knowledgeable about optimization than I am might be able to come up with a stronger theoretical justification for it. But my hacky practitioner's justification is that we're very unlikely to literally be at 0 most of the time.
Okay, thank you.
Yeah. All right, so to zoom in and describe how we actually do gradient-based learning with neural nets in particular, we're going to spend some time looking at the idea of cross-entropy in detail. So this slide is really just an equation. It's an important equation. I'd say it's almost more of a way of life than an equation. And there's basically 2 big ideas that you should get out of it. The first is that most of the time today, at least the way that I personally work and the way I think most other people in the field work, is I don't think of myself as learning a function mapping from inputs to outputs. I think of myself as learning a conditional probability distribution. So we have some input values x, we have some output values y, and we learn a conditional distribution over y given x. The neural net itself will predict some of the parameters of that conditional distribution. Like if y is a continuous valued distribution, is a continuous valued output, the distribution p model of y given x might be something like a Gaussian distribution. And the role of the neural net is to predict the mean of that Gaussian distribution. But we're not literally trying to learn a mapping straight from x to y. We're trying to learn a mapping from x to parameters of a distribution over y. And that changes the way that we'll think about a lot of other things going forward. In particular, one thing that it tells us is that a very nice loss function that we can use almost no matter how we design our model is the cross-entropy function. In probably at least 90% of deep learning applications, you can just use the cross-entropy of whichever distribution you're learning, and you don't need to think about which cost function to use at all beyond that. The cross-entropy is this equation that I've written down here. It's the negative expectation where you sample the inputs X and the true labels Y from the data distribution. In other words, you just load them from the training set. And then you compute the logarithm of the probability that the model assigns to the true label. And so this definition of the probability is going to change the way that the actual cost you minimize looks. But regardless of which model you choose, you're always really minimizing across entropy. And that eliminates a lot of different ideas from your search space for you right away. If we look at the way that different types of data can be modeled with different distributions, and then we look at how we would actually model those distributions with a neural net, we see that basically always using the cross entropy will work out really well for us. One thing we might think about is modeling binary data, like in the XOR problem, where we want to just output a 0 or a 1. To make that example simpler, I actually used mean squared error there. But probably what we'd want to do if it were a real application is we would want to represent the output as a Bernoulli distribution over a single binary variable. The way that we usually represent Bernoulli distributions is we use a sigmoid output layer of the neural net. The sigmoid function squashes the output of the neural net so that it lies between 0 and 1, and you can interpret it as being a probability, specifically a probability that the Bernoulli variable is 1 rather than 0. When we want to train a neural net like that, we actually know right away, just by following equation 6.12, what we ought to use. We ought to use the cross entropy. And we get a particular formula for it based on the fact that it's a Bernoulli variable. The way that you actually implement this in TensorFlow is you take the logits, the inputs to the sigmoid function, and you pass them to TensorFlow's sigmoid cross entropy with logits function. And that will compute a very nice numerically stable function for you that has good, strong derivatives anytime that the model is not already correct. Basically, the only time you get 0 derivative is if you're already predicting the correct answer with very high probability. That compares to if you try to use a different loss function other than the cross entropy. I'll show you in a few minutes how if you used mean squared error here, it would actually not work very well for you. So knowing that cross entropy is almost always a great thing to do can really simplify your design choices when you build these neural nets. If we generalize from a binary variable to a discrete variable with more than 2 values, then we have a multi-Newly distribution over the output. And we can use a softmax layer to represent that distribution. And then there's actually just a different version of the cross entropy function for discrete distributions. In TensorFlow, you would want to use the softmax cross entropy with logits function to implement this. When we get to continuous output variables, then we start to have a lot more choices about how we might actually model them. One really common one is to use a Gaussian distribution. And in that case, we usually just assume that the covariance or the precision matrix of the Gaussian is fixed, and we have the model predict the mean of the Gaussian. Usually to do that, we have a linear output layer, and we just take the output directly and use it as the mean of the Gaussian. If we look at the structure of the cross entropy function between 2 Gaussians, we actually get that it's the mean squared error, or sorry, not between 2 Gaussians, but like between a Dirac for the targets and the Gaussian output by the model. We get that it's the mean squared error, and we can just minimize that. If you want to learn some other components of the Gaussian, like if you want to learn the covariance, this cross entropy function will actually show you directly how to set up the loss to do that. And so it's a very nice way of automatically telling you how you should train each of the different parameters that you choose to learn. If you want to get fancier, you can make other choices about how to model continuous variables. Like you can use a mixture of Gaussians, and then you have a mixture density output layer. I'll show you in a little bit more detail in a second what that looks like. And the really beautiful thing is you can still fit that with cross entropy. So you don't need to redesign your cost function when you use this new output layer type. You can actually go even further, and you could just say you want to learn an arbitrary distribution over the outputs. You can learn any function p of y given x. And you can do that with deep learning. It gets a lot more complicated. You can do it with things like generative adversarial nets, variational autoencoders, and fully visible belief nets. These are all covered in part 3 of the book, and they all go a little bit further than the basic gradient-based learning techniques that we've covered in this chapter, and they have different loss functions.
Question. Yeah. So obviously Gaussian is a heavy hitter in the space of distributions? Is like, would anyone be like a Poisson? I'll see what a Poisson does, or is there just not anything useful there, or is
Yeah, so you may want to use a Poisson for some kinds of data where you have reason to believe that that's the correct distribution. Or for example, Laplace is another one that I actually use occasionally. The reason that Gaussian is so common is that the central limit theorem says if you add up lots of different random variables from different sources, eventually that sum will have a Gaussian distribution. So if you just say like, I have no idea what I'm doing, Gaussian is probably the best default assumption. But yeah, this table is not meant to be exhaustive. This is just covering, this is probably like 95% of deep learning use cases here. But there is another 5 where it's like Laplace, Poisson, and a few other strange things.
I have a follow-up question to Thomas's question. Well, how do you deal with fat-tailed like distributions, like the Cauchy distribution? Would you be able to handle it using one of these arbitrary algorithms?
See, the Cauchy distribution has something funny about it, right? That, like,
Undefined mean and variance.
Yeah. I forget whether that actually causes a problem for gradient-based optimization. That's a bit more of a technicality than I'm ready to answer off the top of my head. In general, you can fit things like a Laplace distribution just by plugging in the formula for the distribution here. And then you're right that in some cases the statistics of the distribution mean that when you try to compute the expected gradient of this, you're going to have like a sum that doesn't converge, and then you're in trouble.
Bimodal.
Yeah. Well, bimodal is usually not a problem. So like if for example, you want to do a mixture of Gaussians, you can do that.
Yeah.
So here's an example of a mixture density network, just to give you a little bit of a taste of if you have a more complicated output distribution. This one has 3 different components, so it's a mixture of 3 Gaussians. And I've actually made it so that both the mean of each Gaussian and the variance of each Gaussian are parameters that the network can output. So you can see over here, this component has a lot more variance than it has over here. The network is actually saying to output high variance here and low variance here. And then the mean of each component is tracking, different outputs of the network that are fed into that component of the distribution. So you could actually fit this 3-component Gaussian mixture to whatever target function you had, just using the cross-entropy loss. And here at Google, Mike Schuster has done a lot of work with that, if you'd like to talk with him. And it's been really good for things like modeling speech waveforms. I mentioned earlier that it would be a bad idea to use the mean squared error loss with a sigmoid unit. And here I'll show you a bit of a concrete example of why. So the x-axis of this plot is the logit, the actual value output by the linear part of the neural net. And then we apply a sigmoid function to it to get a Bernoulli probability. So this blue line here is showing how the probability increases as you move from left to right. It's saturated at the far left, it's saturated at the far right. Now let's suppose that we've computed this output value z for a particular input where the label in the training set is 1. We want the probability of the 1 class to be as high as possible. If we compute the cross entropy between the distribution that has the 1 class selected deterministically and the distribution defined by the sigmoid function applied to z, we get this loss function here, this orange curve. And that's the one that I recommended in the table 2 slides ago. Over here, where your model is very wrong, you're predicting 0 rather than 1, the loss function increases linearly as you move further to the left, as you get more and more wrong. And so the gradient always gives you basically a derivative saying that you should move to the right, proportional to the step size of your learning algorithm. When you get over here, and you've basically got the right answer already, your gradient starts to vanish, but that's okay, because you've already got the right answer and you don't need to update your output. The reason that the cross entropy has strong gradient over here is that your sigmoid function has an e to the x in it, and your cross entropy function has a log in it. So the log and the e to the x partially undo each other. There's other components to the sigmoid that don't get undone by the log, but you get enough of it undone that you get this strong gradient here. Let's suppose we did mean squared error instead. So we actually compute the square of 1 minus the sigmoid value, trying to get the target output value of 1. Mean squared error actually is expressing the right preferences. It does have a value of 0 where you've got the right answer, and it increases monotonically from there. The problem is that it eventually stops increasing very much. So if you look at all of Rn and you think about where is the mean squared error actually informative, well, it's really only informative between like about here and about here. So out of most of space, there's this tiny little spot where the mean squared error actually helps you learn anything. Everywhere else, it's saturating quite a lot, and you would need some kind of complicated second order optimization algorithm to scale it back up and help you learn again. For a long time, people believed that neural nets did not work very well. And a really strange thing is that you can take the description of neural nets from the Rummel-Harden-Hinden paper in 1986. And even with sigmoid units, no batch norm, no ReLUs, they work fine. So part of the question is, why did people think that they worked so badly for so long? It may partly have been that there wasn't enough computation to run lots of experiments and figure out a good set of hyperparameters for each problem. But I think another part of it is that people often try to do things like apply mean squared error to softmax and sigmoid units. And without doing lots of experiments and getting a lot of experience, it wasn't obvious that that was the problem that was causing the neural nets to not behave very well. So one of the few things that we can actually recommend pretty strongly is to almost always use cross entropy. And if you don't want to, you should have a good reason for why you're not going to. And if something goes wrong after you've switched away from cross entropy, you should strongly consider moving back to it. The next part of our roadmap is the hidden units section. And there's really not actually a whole lot to say about hidden units. Most of the time, you can use rectified linear units. And if you want to use something else, for some research projects, it makes sense to get a little bit creative. If you know that you're doing something unusual in your research project and you need to change the hidden units to compensate, that can make sense to do. The main exception that comes up in practice rather than research is if you're using a recurrent network, then there are special kinds of hidden units designed for use in recurrent nets. Those are all covered in chapter 10, and you don't really need to worry about them yet. My last real comment about rectified linear units is that they're, as we discussed in the question earlier, they're not the only thing that works. They're just the thing that we've standardized on as a community. And there are quite a lot of other units that work really well, but they don't really work a whole lot better or worse than ReLUs. When I originally wrote that paragraph in the book, my co-author Aaron Cornville said, well, how can you back that up? I said, so I'm trying to say that hidden units that haven't been published yet also work fine, and it isn't worth publishing about them. So if it had already been published, it would be in the literature, so I couldn't say that a not yet published hidden unit is useful. So I just thought, well, I don't know of anybody who's used cosine as a hidden unit. So Aaron and I actually ran a new experiment just for the sake of making this argument in the book. We just picked the cosine function out of a hat, ran that, and it worked pretty well on the MNIST data set. And so that gives you an idea that basically a lot of activation functions that have strong gradient over quite a lot of their domain are going to work really well in a lot of cases. And a lot of the time when people first get involved in deep learning research, they might try some new function and get really excited that it works really well. I've even done this myself. I wrote a paper about max out units. And over time, we keep finding that there's like less and less reason to believe that they're significantly better than ReLUs. They're better than ReLUs on some tasks, but not consistently better than ReLUs. And over time, people keep finding better hyperparameters for ReLUs. So I even covered max out when we wrote the book a few years ago. As of now, in this lecture slide, I'd say basically just use ReLUs. And most other activation functions we really don't think are consistently adding signal rather than noise. So the hidden units don't really pose much design choice. It's basically ReLUs unless you're using a recurrent net. The cost function is mostly chosen for you. You can pretty safely assume you ought to use cross entropy. The place where you do actually often have to think a lot is the architecture. The basic concerns that we'll think about when we're designing an architecture are the depth and the width of the architecture. So the depth is basically how many layers does it have? The width is basically how many units are there per layer. And for now, we're just covering the basics. Later, when we study things like convolutional networks and recurrent networks in detail, we'll find out that there's all kinds of intense architectural features like convolution kernels of different sizes and inception modules and gated recurrent units and things like that. For this chapter, we're really just going to look at the basic depth and width ideas and not get into some of the more fine-grained details of how we connect the units to each other. The key piece of theory that everyone should know about neural net architectures is that a single hidden layer is enough to represent any function to an arbitrary degree of accuracy. So when I say represent, it's important to understand what that means. It means that if you pick a particular set of parameters, you can express the function that you want by setting the parameters of the net to those parameters. It does not mean that you can learn the function that you want. Your optimization algorithm might get stuck in some kind of situation where it can't update. If, for example, if the Hessian matrix is very poorly conditioned, your learning algorithm might spend forever trying to approach the correct function. Or you might find that the function is so noisy that you can't really make your batch size large enough to successfully fit it. Or you might get stuck on a saddle point or something like that. So the universal approximator theorem is just saying, out there exists a neural net with parameters that fit some function. It doesn't necessarily mean that you can learn it, either in terms of optimization or in terms of statistical generalization. But we do know that you can actually write down a neural net that represents what you want. So then the main question of designing an architecture is, why would we ever go deeper than one hidden layer? If the universal approximator theorem tells us that we can go deep enough, or that we can represent any function with just one hidden layer, why do we need more? The short answer is there are two reasons. One of them is essentially a computational reason. The universal approximator theorem tells us that one hidden layer is enough, but it doesn't tell us how many hidden units we need in that layer. It tells us the minimum depth, but it doesn't tell us the minimum width. It turns out that for depth 1, the width required might be exponentially larger than for some greater depth. So that's basically a computational reason. You don't want to spend a whole lot of time computing the values of exponentially many hidden units, and you don't want to spend a whole lot of memory storing the parameters for those hidden units either.
Why is it exponential?
It's problem dependent. So depending on which kind of function you're trying to learn, it may be exponentially more or it may not. And then there's papers that we cite in the book that link to proofs about specific problem classes where they show that there's an exponential blowup if you use too little of depth. I don't know enough about those results to give like a 5-sentence intuitive reason for why it has to be exponential.
So this is not mathematically proven, but it is more observed from the experiments.
It is mathematically proven.
Oh, really?
I just mean it's mathematically proven, but I don't know of a short intuitive description of how the proof works.
Nice.
Yeah.
Okay.
So it seems to me this is sort of like a lookup table, right? In that you can kind of map anything, map an arbitrary function with an arbitrarily large lookup table, right? Is that kind of how I could think about this theorem?
Yeah, I think the way that the proof is actually structured is basically saying you can eventually make a lookup table. The way that the networks work in practice doesn't really resemble the construction that the proof uses. So I don't think of regular neural nets trained with gradient descent as learning lookup tables.
Yeah, but this single layer version is basically saying you could express any function, any function using a lookup table. You just wouldn't know how to populate the table.
Yeah.
Which is the learning part, right?
Yeah.
Okay.
Well, and I mean, you depending on which hidden unit you're using, it is pretty obvious how to populate the table. Like if you use, I didn't mention it in this lecture, but there's a hidden unit called the radial basis function, and you can turn it into more or less like something like an indicator function. And so then you could just say, I'm going to make a different radial basis hidden unit centered on each of my training examples. And And then if you just put weights for each class on the corresponding training example, you'll more or less fit the training set. To some extent, that's the way that kernel machines work. The way that I described it is sloppier than how they actually work, but like a support vector machine with an RBF kernel is basically this kind of lookup table. And a lot of what neural nets are trying to do is to make a model that has that representational capacity but generalizes better to new data. The other reason that we might want deeper networks is that the shallow network might overfit. And a deeper network actually, for one thing, if we can get away with fewer units per layer, then there's fewer parameters to learn. And so just statistically, it's easier to get an estimate of the value of any one parameter. But also the deeper net is essentially locking us into a prior belief that the function we're trying to learn can be defined by one set of variables referencing another set of variables. And a lot of the real world has this structure. Like trees have branches, have leaves, and so on. Or buildings have rooms, and then there are people in the rooms. That lots of the tasks we might want to solve with AI actually do have this kind of structure where you keep zooming in and seeing another granularity of detail in the problem.
So flip side of this question is that why don't we just make the narrow network deeper and deeper? Is there any overlap with that?
Yeah, so the other question is like, why not make the net deeper and deeper? Well, usually, if you wanted to make it infinitely deep, then it could represent the right function, but the computational cost would be too high. And I guess if the question is, what if you wanted to give it like width of 1 and some very large depth? There becomes this problem of like an information bottleneck. That if you have 1 million input features, you probably don't want to summarize those with only one value in each layer afterward.
Nice.
You can come up with really funny proof constructions where you say all of my values are real numbers, and then you can just embed as much information as you want in the infinitely many digits of the real number. But when you actually implement things in a computer, or when there's noise in the computation, even in theoretical models, then you really want to have a large number of independent numbers describing the layer below. One way that you can think of the effect of depth is you can think of each ReLU as learning like a way of folding space. And so you can start out with very complicated decision functions, and after you've folded them, they become simpler and simpler. So after passing through several folds or several layers in the net, you end up with something that's easy for a linear classifier to describe. In the text, we reference a paper that describes actually how many different regions you can specify. And essentially, the deeper the net, the easier it is to specify lots of different regions. So that's the computational side. On the generalization side, these are some experiments that I ran while I was at Street View. We were using a deep convolutional net to transcribe multi-digit address numbers out of photos from the Street View car in order to place those buildings on the map. On the x-axis here, we show the number of layers. This is back in 2013, so we weren't using nearly as many layers as people use now. We found that the test accuracy basically always went up as we increased the number of layers. Eventually, we ran into diminishing marginal returns, and eventually it became a little bit hard to optimize this network, and we would just underfit on the training set. Today, in 2017, we have additional techniques like batch norm and the ResNet architecture that make it possible to optimize much deeper nets and continue to get this dividend that comes from greater depth. You might look at this and say, well, you're saying that depth means we generalize better. Maybe it's just that larger models generalize better. So we also ran an experiment where we changed the width of the network while keeping the depth constant. So we did this for a depth 3 convolutional net, a depth 3 net that had a fully connected layer, and a depth 11 net. And well, basically you can see the depth 11 net was always better than the shallower nets for several different values of the parameters. We did actually find the depth 11 net worked pretty well if we just made it really big. But you can see, for example, the depth 3 net would overfit if we made it bigger, that the error would actually the accuracy would decrease as we increase the number of parameters by widening this net.
Does it go back up at the end of that? Or is that just
Yeah, I mean, it
is
doesn't
that just
go up.
noise?
It doesn't go up higher than it started, but yeah, I mean, with any single measurement, you can always expect a bit of statistical wobbling around.
Okay.
And so that's the basics of architecture design. Is depth will usually help you more than width. You want to make sure that you have enough depth and width that you can fit the problem. And as you make the model bigger, it's usually better to make it bigger by making it deeper. Yeah.
So when you have a lot of hidden layers, are they usually uniform width, or is there any guidance on how you pick the different widths?
It depends a lot on which kind of model you're training.
Okay.
And that'll make more sense after you've seen later chapters. Some kinds of convolutional nets, like AlexNet and Inception, are more or less forced to change size as you move through the net. Other kinds, like ResNets, are more or less forced to stay the same size as you move through the net. And so a lot of the time, the exact width of each layer will be determined by some of these considerations that are forced on you by the other aspects of the design.
Okay.
For like a fully connected net where you're really free to choose the width of each layer individually, I usually just keep all the layers the same width. And that's usually just because the amount of time it would spend me to search through different options for each layer individually is not worth the payoff that I get. Usually there's a pretty big payoff to searching over the depth and a pretty big payoff to searching over the width of all the layers, and then a smaller payoff to searching over the width of the individual layers. Okay. Another thing that you should think about when you're making a decision is how long are you going to keep using the same model? So this is like a model that you're using for a research project, and you're just trying to get an answer to some question that will inform, a paper that you'll write or will inform your future work. Then you probably don't want to spend a whole lot of time optimizing it, because getting something pretty good will be enough. If this is like a model that you want to serve to 1 billion users every day, then you probably do want to optimize to try to reduce the amount of electricity you'll use and things like that. And so then you might spend more time seeing if you can get away with shrinking any of the individual layers.
Okay. Thank you.
Yeah. The last part of this chapter on feed-forward nets is about backpropagation. We want to fit these models using gradients, so we need to actually get a gradient somehow. The backpropagation algorithm is really simple. It's actually, you could say, I put it in scare quotes, but you could say that it's just the chain rule of calculus. And so essentially, if you've got some input variables x and some output variables z that have some intermediate variables y that were used to compute z, then you just add up all the different dz, dy, dy, dx terms. And I've listed here both the scalar and the vector version of the chain rule here. The main thing about the backpropagation algorithm that is the reason that I have the scare quotes here is that backpropagation is a particular implementation of the chain rule. You want to make sure that you don't waste all your time recomputing the same value over and over and over again. And a naive implementation of the chain rule would do that. So backprop actually uses a table filling algorithm to make sure that you compute each of these values just once. There is a speed versus memory trade-off here. Backprop basically says, let's compute every value only once. But there's other versions where you could say, we'd like to use less memory, even if we have to compute things a few times. There's a technique in the automatic differentiation literature called checkpointing, where essentially, instead of storing everything, you store like every nth value that you see. And you might have to recompute up to n things to compute some of your derivatives, but it uses less memory. The basic idea of backprop is to make this table filling algorithm where if we want to compute the derivatives of some loss function applied to some output y of a neural net, we start by doing forward prop, where we begin with the input values x, we compute the hidden values for different layers, we eventually compute the loss and the derivatives of the loss, and then we move backward through the net. So I mentioned this was a table filling algorithm. Some of the things we fill in the table are actually the activation values of the neural net on the way up. We'll reuse those when we compute the derivatives on the way down. And then on the way down, we look at the stored activation values from the forward prop, we look at the gradients of the layers above, and we use them to compute the gradients of the layers below and the gradients of the parameters of each of the layers as we work our way down. And so if your neural net takes the form of a chain, you really walk forward through the chain to compute all the activations, and then walk backward through the chain to compute all of the derivatives. And that's why it's called backpropagation. In things like Theano and TensorFlow, we describe these with computation graphs, where we have nodes representing different variables and edges describing how we apply operations to variables. Sometimes you can make a graph with two types of nodes where operations and variables are both in the graph. The basic idea is forward propagation can follow these arrows forward through a graph. And I've shown you several different example graphs for different kinds of models here. Backpropagation follows these arrows backwards through the graph. And each op essentially defines how you compute the derivatives on the inputs to the op, given the derivatives on the output, and possibly given the stored activation values for the inputs to the op on the forward pass. The main thing that the backprop algorithm gets you by using this table filling strategy is that you will find that you will often compute the same thing over and over again, and backprop will just store it once rather than recomputing it. So here we've got this chain graph where we apply some function f to several different variables. We just, we compose f several times. So the input I'll call w, we compute f of w and get x, we compute f of x and get y, and so on. We actually write down the derivative of dz dw using the chain rule. We find that this f of w term appears twice. And the backprop algorithm would just cache that as the value x. The naive implementation of the chain rule would have us compute this f of w value twice. This is a really simple example with just 4 nodes in it. And so there's just one value that's repeated, and it's only repeated twice. In something as big as a neural net, you could imagine that there's an explosion in the number of things that would be repeated if you didn't have a table filling algorithm keeping you on course. Libraries like Theano and TensorFlow use what I call symbol-to-symbol differentiation. You give them a computational graph describing an expression, and they will build an additional computational graph for you describing a derivative. The really nice thing about this is it means that your language of computation is closed under differentiation. Your derivatives are the same type of object as the original expression you used. So you can then go ahead and compute second derivatives as well. Some languages will take a description of an expression, and then they'll give you an actual numeric value for the derivative. And it's just like an actual float 32 value that you can't differentiate a second time, so you don't have second derivatives. This is what the computational graph for a pretty non-trivial neural net loss function looks like. Since we're getting low on time, I won't actually walk through it in a lot of detail. But if you'd like to take a look at the slides or figure 6.11 in the book, you can see exactly how we compute the weight decay and everything. And you can think about how backprop would trace these arrows forward in the forward prop step and then back in the derivative creation step. Finally, I mentioned that we can compute second derivatives. Usually what we actually want is some information about the Hessian matrix as a whole. The Hessian matrix is usually not feasible for neural nets because we might have millions of parameters. And that would mean that the Hessian matrix has billions of entries. It could be very expensive even just to represent, let alone to compute it. What we can often do instead is we can compute the product between a Hessian and some vector of our choice. It turns out there's a very simple trick where we can compute this using differentiation, where we can essentially take a gradient of a function, multiply it by a vector, and then take the gradient of that dot product. That will actually, if you do the math and work it out, that gives us the product between the Hessian of the function and the vector that we chose. So you can use this for things like taking a second derivative in a particular direction in the input space of a function. And it's often very useful for designing more sophisticated optimization algorithms, like second order optimization algorithms, or just for doing complicated analysis to understand what your models are doing.
So is the complication there picking the direction to do the optimization?
Yeah, definitely.
Okay.
Yeah, because there's quite a lot of directions in this
Right.
high dimensional space.
Yeah. Okay.
So that's all of the content. I think We've reached the end of our hour. I'm not sure if we're about to get kicked out of the room. I'm fine to stick around for a little bit if people have further questions.
Thank you.
Very welcome.
Are we still recording or is it?